what it is that was going on with our experiment. I brought along, just so you remember, I brought along a Kuntz tube, and you recall we were holding the tuning fork right here, moving the piston until we reached resonance, the loud sound, resonance. What we were doing was establishing a standing wave inside of the Kuntz tube. We're going to think of the sound wave as a transverse wave by plotting pressure as a function of displacement. And of course, the end of the Kuntz tube that has the piston in it is a place where no movement is allowed to take place, because the piston's there. The open end where the tuning fork is vibrating, we're going to get maximum displacement there. So I drew a sketch, a rough sketch, very rough, about what's going on over here. And so let's pretend like we found 3 different locations where we have a resonance. When you have a resonance like this, the tuning fork is here, it's pumping energy in this area, so you're getting maximum movement here. By the way, that's called an area which is an antinode. And virtually no movement of the air at the piston, that's called a node. So node, antinode. The question is, we don't quite know what the picture is. There's an antinode at the opening, there's a node at the piston, and we don't really know how many wavelengths fit in there. So I just said, well, it's x times lambda, whatever x is. The picture I've drawn here, of course, is 1 1/4. X would be 5/4 lambda. But we don't know what the picture looks like, and there may have been more waves or fewer. However, the very next point of resonance is when the picture would look something like this. Notice that the next point of resonance is an antinode here, a node there, and this time what I've done is I've added a half a wavelength. So as soon as the piston has moved a half a wavelength further, then we find the next resonance. And likewise, the third resonance that I show here is we move yet a second half wavelength further. It's a full wavelength, but I emphasize it by saying second half wavelength. So really what we've done is to measure the wavelength of the sound wave trapped in the tube by finding several resonances. Each one should be approximately a half a wavelength away from the previous or the next. Well, all I'd like you to do is to determine the speed of sound in the room. The speed of sound is simply the wavelength times the frequency. So you chose a tuning fork that has a stated frequency. You have now measured the wavelength, calculate the speed of sound. You'll find in your book that it's probably somewhere approximately 330 meters per second. So hopefully you've gotten 3 different frequencies and 3 different sets of wavelengths from which you can estimate the speed of sound for each different tuning fork. So by looking at your data, that is by looking at the overall length for each resonance, the difference between them will be half the wavelength. You've got the stated frequency, which you can accept as being like gospel truth, because it's pretty bloody accurate compared to your wavelength measurements. The wavelength measurements where you're using your thumb and your ear aren't very accurate. So we'll just take the stated frequency as a perfect frequency. You're measuring the wavelengths. Measure the wavelength several times for each tuning fork, and then probably the best thing to do would then be to average that wavelength plus or minus a reasonable uncertainty, which could be based on the range of your values. If you're getting wavelengths like let's say you get lambda is 10 centimeters for the first run. The second run, you get 12 centimeters, and the third run, 3, you get, I'll make it easy, 8 centimeters. Then I would say that the average lambda for this would be, of course, 10 centimeters plus or minus 2 centimeters. So I'd make an estimate like that. It's kind of pessimistic to say that the tolerance on your measurement is as big as the maximum uncertainty. But with this crude of an experiment, that's a perfectly acceptable way of doing it. So the actual calculations should be fairly easy. Probably the most important thing is, did you get a reasonable wavelength? One thing that's perfectly acceptable to do is walk around and see if other groups use the same tuning fork you did, if you got the same wavelength. If not, you've still got Kuhn's tubes and tuning forks. As you recall, it only takes a couple of minutes to remeasure things. So give it a try, do your calculations now before you do any write-up, do your calculations. If you're within the ballpark, good. If you want to try your tuning fork again, let's do it in the next few minutes. I had a question, go ahead.
How do you determine the wavelength when it could resonate at any one of the
Because each one is half a wavelength away from the other. So you measure one, you measure the next, the difference between those two is a half a wavelength. The next one should be two half a wavelengths.
So we only got two resonants that we were able to hear, and they're so far away, we're just assuming that they're half a wavelength.
And see what answer you get. If you don't come up with a good answer, let's get the tuning fork out and try again. It only takes a few minutes. Any other questions or comments? Then we'll redo it when the tuning fork does have a frequency. You picked up one of the ones that's supposed to be an unknown, which we use for exams.
Well, it had a letter on it.
Okay, maybe you know somebody, maybe a musician, anybody here?